Thanks for the invitation. So I'll get straight to the point. I will talk about Benjamini-Schramm convergence of arithmetic. Actually, 3 manifolds. So let me start by defining Benjamini-Schramm convergence and its sister property that from representation theory, namely limit multiplicity. Okay, so in our setting, G will be a semi-simple group. So X, this will be a symmetric space. And gamma I, this will be a sequence of lattices. In G. Okay. And I will say that this sequence is non-trivial if there are no infinite repetitions. So we say that Benjamini-Schramm convergence is a convergence of metric spaces. In the setting of locally symmetric spaces, we have a simple definition. So we say that sequence of locally symmetric spaces X over gamma I converges Benjamini-Schramm, so I write it like this, to X if for every positive R, think of this as a radius, so for every positive radius, the limit while I goes to infinity, the volume of the thin part of this orbifold, R thin part, divided by volume of the whole orbifold, goes to 0. So that means that locally most of the space looks like the covariant space. Okay? So that's basically the definition. So Benjamini-Schramm convergence was first introduced by Benjamini and Schramm for regular graphs. And it was studied in the setting of locally symmetric spaces by 7 samurai. So whenever I write 7 samurai, that means the set of authors are the original. Now it's getting harder. Mikolaj Fraczyk, and last one. Jean? Yes. Yeah. So they investigated this notion in the setting of locally symmetric spaces, and they proved 2 important results. So,
sequence X on gamma I Benjamini-Schramm converge to anything apart from X or some X on gamma?
yeah, okay. Does it work? Okay, so Yeah, they can converge to something else, but in general, this won't be a single space, but probability distribution on isometry classes. So all isometry classes of rooted metric spaces form a, correct me if I say something stupid, compact space with Hausdorff topology. And in general, limits, Benjamini-Schramm limits are measures on this space, probability measures on this space. And in our case, this is just a Dirac mass in isometric class of X with some distinguished point. X is, yeah, it's homogeneous, so choice of the point, it doesn't matter. Okay, so they prove two theorems. So first thing, that if G is higher rank, that means real rank is at least 2, and has property T. So we know that higher rank groups in general have property T, but this covers the case. I think this is to exclude products of spaces of rank 1 without property T. If G is higher rank and has property T, then for every non-trivial sequence gamma I, this sequence of orbifolds converges Benjamini-Schramm to X. Okay, so this is very general. They don't have to be commensurable. Nothing. Just we cannot have infinite repetitions. And 2. So if G is any.
You see infinite repetitions.
Sorry.
What's that up to?
So I want to exclude the sequences where we have like single lattice repeats infinitely many times. Yeah, by a single lattice I mean conjugacy class. So identifying conjugated lattices. Second thing is if G is any semi-simple group, gamma 0 is arithmetic lattice, and gamma I is a sequence. Okay, we don't have to deal with sequences here. So gamma 1 is a congruent subgroup. So think of this as, for example, this is SO to Z. Those are matrices in SO to Z which are congruent to identity modulo N. So in that case, we have something stronger than Benjamini-Schramm convergence. Then we know that the volume of thin part is smaller to some constant than exponential some constant C times R times the volume of gamma 1 x over gamma 1 power 1 minus delta. And now what do we know about constants? So let me write instead of this C1, C2. So C1, C2 depend on gamma 0 and delta positive. It depends on G. So here we have something stronger than just Benjamini-Schramm convergence, because we know by Borel and Prasad that if we have congruence lattices, then if the sequence of congruence lattices is not trivial, so there are no infinite repetitions, then their volume has to grow to infinity. So if we divide volume of thin power by volume, we get some constant times volume to negative power, and by Borel Prasad this has to go to 0. Okay? So this we want by yeah, but this works for SL to R too, also, and SL to C. So Wong's theorem says that if our group is not isomorphic to isogenous to SL to R, SL to C, then there's only finitely many local symmetric spaces below given volume. But this theorem is valid also for SL to R, SL to C. So I have to use like analog for Wong's theorem for arithmetic lattices, for congruent lattices.
So again, there is a restriction on the sequence gamma I, that there are all congruent subgroups of a given arithmetic lattice. That's it? That's the assumption?
Yes. In here, if we want to translate to a statement of sequences, there will be all subgroups of a given, congruent subgroups of a given lattice, arithmetic lattice.
There is no...
Because here we don't have to deal with sequences, we have explicit inequality, which would imply Benjamini-Schramm. So for Prasad, this.
But here, again, yeah, congruent subgroups in a fixed arithmetic lattice. I have it right. In this state, yeah, they depend on gamma.
Yes, those two constants depend on gamma. Okay, now I think I can. So there's something about limit multiplicity. Are there any questions regarding this point?
So the volume grows how?
Volume,
Yeah, if you take
if by Borel Prasad says that it goes to infinity if we change arithmetic lattices inside a given Lie group. So how to translate this statement to
no,
statement about on Benjamini-Schramm convergence?
no, that I understand. It's just a dependence on.
Oh yeah. Okay, this is overkill. I understand. We don't have to use Borel Prasad. We can, since we are dealing with subgroups of a given arithmetic lattice, we can just observe that if we change the conjugacy class infinitely often, then index goes to infinity. So that's it.
Yes.
Okay, so this implies Benjamini-Schramm convergence for sequences of congruent subgroups of a given lattice. Okay, so limit multiplicity. So if gamma in G is the lattice, then G acts on L2 of G over gamma by right translations. So let's write our gamma for this action. Explicitly, our gamma G of some phi of x, this would be phi of x. Okay. So now we'll consider spectral decomposition of this unitary representation. So, if gamma is unitary, uniform, then we know that L2 of G over gamma can be written as a direct sum of its irreducible subrepresentations. So big pi of G will be unitary dual. So each of these representations has some finite multiplicity. I will denote it by m gamma phi times phi. Okay. And we need, for this we need to know that gamma is uniform. Then we have a discrete decomposition. Otherwise there is continuous part. So now for every lattice, we'll construct a measure, not probability measure, but a measure, which lives on the unitary dual. So mu gamma, this will be by definition 1 over volume of G over gamma times sum over all irreducible unitary representations, multiplicity of pi and gamma in L2 G over gamma times direct delta in phi. Okay, this is a measure. On unitary dual. And now we can define limit multiplicity property. So if gamma I is a sequence
What's the total mass of mu gamma?
infinite.
It's infinite, and it's not a probability.
No,
It's a
but
measure.
there is a topology on topology on this G.
Yes.
And it's locally finite.
So what do you you normalize by the
I normalize
by
by
the
the
volume
volume.
for other purpose, not for the purpose of having.
Yeah, I do not this. This is has infinite mass. There's countably infinitely many representations inside this space. So if gamma I is a sequence of that uniform, lattices in G, then this sequence has property, has limit multiplicity property. If and only if this sequence of measures mu gamma I converges with the start to partial measure. Partial. I will, so instead of defining partial measure, I will just rewrite this condition in more understandable terms. because I would have to, otherwise I would have to define topology. We call the definition of topology. Unitary dual. Proved in 96 that this is limit multiplicity property is equivalent to the following. So for every f continuous smooth compactly supported function of G, the trace of R gamma I f. So this is convolution by f on the space L2 of gamma I over G over gamma I. So the trace of this guy, normalized by volume. This has to go to F1. So this is statement equivalent to
So this operator is a trace, has a trace?
yes,
So we are in
if
two dimension. I mean, which?
it's infinite dimensional, but the fact that it's smooth and compactly supported is enough to show that this has a trace. Yeah, and we recall that we are in a uniform case, so manifolds are compact. So that's not, otherwise it would be a trace class. Okay. So now let me state a few theorems with relations between those two notions. So 7 samurai. They prove that if gamma I is uniformly discrete, that means the indicator radius of all those manifolds, all those orbifolds, gamma I over x is bigger than some constant bigger than 0, then Benjamini-Schramm convergence implies limit multiplicity property. Okay.
So is there a characterizing property for the Plancherel formula, which is relevant to this? I mean, why do we expect a Plancherel formula to show?
Okay, so
to show F?
I can explain it. So the reason for that is the following. So this, we can observe that the trace of gamma I f over volume can be rewritten as integral over unitary dual of trace of pi of f. This is true what that is. It's for every pi of f d mu gamma I, right? By definition of this measure. On the other hand, Plancherel satisfies the following property, which is a defining feature of Plancherel measure. So for every f like this, like in measure, we have f1 is equal to same integral but with functional measure. Okay, so now we can observe that.
No, so this explains the relation between the two statements, but
Yes.
not exactly why the Plancherel formula should arise. When we think as gamma I as
Oh, okay.
being bigger and bigger.
Why should it arise? Because
I mean, this is G and
so if lattices are okay, why this should be reasonable. So
yeah,
if your Benjamini-Schramm sequence of lattices is Benjamini-Schramm convergent, then it means that around the typical point you don't see the manifold structure. Okay, so if you pull it back to gamma I over G, G over gamma I, and that means that in this quotient space, large balls look like balls in G.
yes,
So when you think about convolution with compact support, is on those large balls, this operator acts exactly like convolution on G.
yes,
So this contribution to the trace, it should be F1, because on G, naively on G this trace is infinite, but if it were finite, it would be integral over G of F1, right? If G were finite, then this trace would be cardinality of G times F1. So now this space gamma G over gamma I is finite, has finite volume. Most balls look like balls in G. So for those points where we don't see where in our balls we don't see the lattice, the contribution to the trace is F1. So roughly the trace should be integral over arctic part of F1, which is roughly the volume of the whole manifold times F1. So that's why we should expect this. We need to uniformly discrete lattices because the very thin parts can have huge contribution to trace, even though they're supported on a subset manifold of small measure. So they won't destroy Benjamini-Schramm convergence, but they can significantly change the traces. Okay. For the converse, so I'd say that this is folklore, but I haven't seen it done in any article. So limit multiplicity property implies Benjamini-Schramm convergence. And again, why? Because limit multiplicity property says that trace, like the topology of this quotient space, doesn't contribute to the trace. When we convolve with F, we take average over some. Let's imagine that F is a characteristic function of a ball, and convolution with F is taking average over this ball, average integral over this ball. And if limit multiplicity is true, then trace should be F1 times the volume of the manifold. So those points where this ball overlaps itself, they cannot happen too often because they would bring a positive contribution to the trace. So points, what I'm trying to say is that points where injectivity radius is small can be detected via convolution with some characteristic function of some balls.
Is this for not assuming uniformly discrete one?
Here, no. This is true without uniform discreteness, but I have to stick to uniform lattices to to properly define so that they have a chance to have limit multiplicity property. In literature, there is also definition for limit multiplicity property for non-uniform lattices, where they cut off the continuous part of the trace, but in that case, I'm not sure this still works. Okay, for uniform lattices. So now I can state my results. So you see that we have seen two theorems by Seven Samurai. One was about high rank groups, the other one was about sequences of congruent subgroup lattice lattice. So I tried to bring them together in rank 1 case. So I wanted to say something uniform about all congruent lattices with explicit estimate on the size of thin part, but without assuming that they are all lie in a single lattice. So let's say A. This would be the following theorem. So let's GP SL2. In fact, I work with PGL to R. To C. Then for any congruence lattice, congruence. Congruence lattice. I have okay. Then now I have to add some conditions on this lattice. So uniform. Uniform torsion cream. That's it. We have the following bound. So volume of the R is positive. Volume of R thin part. Is smaller at the constant that depends only on R. Then volume of the whole manifold. Power 1 minus delta, and delta positive. I can tell that delta I can take delta bigger than 0.004. Probably not optimal, but sometimes people expect that we could have 2/3 here, and this is not true. This is that's the first theorem. Now that we have here congruence assumption, it's important. So remark is not true for non-congruence. Arithmetic. Lattices. Okay. So the example that we can look at is a sequence of cyclic covers of some arithmetic hyperbolic surface. And you more or less see for cyclic covers that size of thin
What
parts.
does congruence mean?
I will explain it in a moment. It's so if gamma is SL to Z, congruence means that they contain principal congruence subgroup.
How can this be uniform?
Because for every arithmetic lattice, you have a properly defined notion of congruence subgroup. That always means that
Fix a lattice and you consider
only
certain of its subgroups.
So for every lattice, I can say if it's congruence arithmetic without fixing anything beforehand.
Ah,
I don't need to work inside the fixed lattice. Being congruence is a, well, like, intrinsic notion.
I see.
So, but I can say something for non-congruous.
So you said the constant depends only on R, not on the
Yes, only on R, not on the-
structure or-
Like, it also depends on G, but here we have two G's, so.
Yeah.
Okay. So B, this is the same thing, but in limit multiplicity setting. So, same assumptions. Then, so limit multiplicity wants this to be close to F1, so we have similar inequality on the difference between those two. So we have a trace of R gamma. Okay, I have to add some right with F. So F is a compact is supported smooth function on G. In fact, I leave smooth just to know that trace of pi f is always finite, but this statement that I'm about to write is also true for non-smooth functions. Right. Yes. Okay. Let's put f is bounded by 1. And support of f is contained in a ball of values r and identity. Then I have the following bound, so trace r gamma f over volume g over gamma minus f1. This is smaller, constant depending only on r. And then volume of g over gamma power minus delta with the same delta as before. But in proof, I first prove this statement and I deduce this one. Theorem B applied to F equal so one characteristic function of following set. So I need to take the ball out K, maximum compact cycle radius R. One to be safe implies theorem A. Okay. And
Not very continuous function. F is a continuous.
you're right. Sorry. Yeah.
Or a smoothing of that.
I have to smooth out.
Yeah.
So I take some pi, and this pi is not. to internal, and the diameter of its support is smaller than C. This is something for non-congruent subgroups. So if G is, as before, S2 R or S2 department, sorry, PGR2. Okay, this PGL is not very important, but you see that in SL2 we have non-trivial center, and just if the subgroup contains this center, this could destroy limit complexity property for CD reasons. So that's why I'm working with group which have trivial center. If G is one of these groups, and gamma is arithmetic, uniform torsion free, then we have the following bound on the volume. So volume of the thin part. Here I cannot put some power of volume, but I can put volume times, and here we'll have some coefficient that depends on gamma. This will be delta k minus alpha, and I will explain in a moment what those are. So
you mean in A, the groups were not
yes,
the same?
in
So in A and B, this
In A and
G
B,
is
they're-
different from these two, right? Or what?
G is the same. I just the difference is that this is not necessarily congruence.
Ah, okay.
Not necessarily congruence. So K gamma, this will be the invariant traceable gamma. So this is Q of traces of adjoints gamma, and okay.
So how relevant was it in the equivalence of Sauvage that the function was smooth? I mean,
Because Sauvage, you have seen it in that there was some integrals over pi of g of some functions, and for those are traces of pi f, and pi f is of trace class if f is smooth and complex supported. So for example, if f is smooth and complex supported, then we know that pi f is of trace class for every irreducible representation pi of g. That was proved. I know that the results from it's a consequence of work of Harishchandra. So Jean needed that to make sense of those integrals. But just the trace of R gamma is defined as long as pi is, as long as f is completely supported and bounded and measurable.
Well, I knew the definition of the invariant trace field as being Q trace of gamma square. So the same thing.
Yes, this is. For SL2 is defined as what you said, but if it's SL2 then as a trace at gamma is 2 plus okay, and this delta is discriminant, field discriminant. So it measures complexity of this number. And what we know about those field discriminants, so they are generally large, alpha. They're generally large, and we have bound due to Odlyzko. Odlyzko proves that, I think it is, I'm not sure. It's known as Odlyzko bound. Odlyzko proves that discriminant of a field K is bigger than exponential of 60. Sorry.
Any number field now?
Yeah, in a number.
Any number field.
Yes, for a number. This is bigger than 60 times 60 power number of real places. So 6 times 22 power number of complex lists. So it's big. It grows exponentially in degree of the trace field. So let me mention one of the corollaries of this last result. If gamma is arithmetic portion 3 then in portion 3 in SS2 think then this manifold M equal to H3 divided by gamma admits triangulation
Uniform lattice.
sorry?
A uniform lattice.
Gamma is not really necessarily because, okay, from my result, it's true for uniform lattices, but it was known for non-uniform before. So you can combine those two to get statement that's true for any. Right? So it admits a triangulation T with big O of volume and vertices. take degree of the degree of every vertex bounded by 145. Okay, this question whether it's true is known as Galander's conjecture for arithmetic hyperbolic three manifolds. So if you see, we can prove that we can construct those triangulations with a number of vertices proportional to the volume.
There are triangles with tetrahedra which are long and thin in the thin part.
Yeah, you can have like very small triangles in the thin part, but the thin part is so small,
Yes.
like this, like that they will be dominated by the number of triangles in the thick part. Because number theory allows us to control the systole of those manifolds in terms of the trace field. And in fact, the systole of manifold with trace field K of degree D is at least 1 over log D power 3. So I can write it. Two ingredients that I use prove this. Yeah, I will have to finish it soon. First is that the injectivity radius M, length of shortest closed geodesic, so the systole is bigger at a constant than log degree of K then over Q power minus 3. This is a consequence of what? Of the Proposky theorem. The theorem on Mahler measures. Of algebraic numbers. So it was, I think it's Edward de Provence. Of course, he didn't think about manifolds, but from his work it can be deduced that this is true. And second, ingredient of the zone. Right. C. This is so C that controls thin part, and we construct C as a nerve, of a cover M by balls of varying radius. So this cover looks like this. If this is our manifold, then we take big whole sphere, radius 1, but our radius drops as we approach the thin part. So cubic take. get bigger as we go into the thick part. So now, okay, those radii of those balls are always smaller than injectivity radius over 5. So radius at x is smaller than injectivity radius at x over 5. So that in that way we know that there are no overlaps. So the ball cannot overlap itself, and also there won't be pathological situation where we have two balls which are touch each other and they in an like intersection of some number of balls is not simply connected. So if we assume that the radius of those balls is always smaller than injectivity radius over 5, then for every intersection of those balls it will be always contractible. That means that our cover will be a good so-called good cover, and for good covers their nerve is always simplicial complex that is homotopy equivalent to equivalent. And we see that theorem C says that this part, this thin part, is very small. The Dobrowolski theorem says that those balls have radius bigger than some inverse power of the logarithm. But since we have quantitative control on both of these, we can estimate the number of triangles in this thin part, and that the proof works. Okay, so let me just finish. Let me just mention some extension of this result to torsion case and non-uniform case that we obtained with Jean and Bob. So using a soft approach, we show that if lemma is a sequence of arithmetic congruence lattices in a again, it's either PGO 2R or PGO 2C. Then the associated sequence of local symmetric spaces converges Benjamini-Schramm to X. So no assumptions on torsion, on uniformness. But on the other hand, we just get Benjamini-Schramm convergence without explicit estimate. Well, I would like to very briefly tell you what's the idea of this approach, because it's not very deep. It combines what I did for in the uniform case with the methods used by Seven Samurai. The idea is to consider invariant random subgroups induced by gamma i's. So if gamma is lattice, then we can define an invariant subgroup of gamma I. So invariant random subgroup is the probability measure living on the space of all subgroups that is invariant under conjugation. So this is 1 over the volume of this lattice times integral Dirac delta in gamma I conjugated by G. And this is probability distribution on subgroups G invariant and conjugation. So this is our IRS, for those who've seen it before. And the seventh samurai, they proved that Benjamini-Schramm convergence of a sequence of quotients by those lattices is equivalent to some statement of convergence of those measures. In fact, that's how they prove their theorems. They translate it to statement of convergence of IRSs. So the summary, they say that this convergence, Benjamini-Schramm convergence to X is equivalent to weak convergence then there is some topology on the space of those subgroups called Schoboty topology. So this is convergence of measures in this topology, weak topology in this convex topology. This has to converge to Dirac delta in the trivial subgroup. This trivial IRS. And so by combining methods that work for proofs, combining methods for proofs of ABC. We show that any limit, so any mu which is a weak limit of gamma i's, it almost surely it consists of subgroups supported subgroups which are very special, so containing only torsion and unipotent elements. Okay, but in particular, those are in particular non-zero students. They are non-zero students. Okay, so we show that any limit of those invariant random subgroups is supported on subgroups that are not zero students. And on the other hand, 7 samurai to show Borel density for irises. To show that if mu is not trivial, then it is Zariski dense. With positive probability. Okay, this doesn't make sense now. So mu is a measure, so it's if it's not trivial, then it gives positive mass to.
In the case SL2 of C, can you really get an infinite order to be unipotent or just parabolic? I mean, you could have a combination of the two. Can you exclude from scratch?
Parabolic, you mean
Combining
torsion,
unipotent and torsion, so -1
for example.
in SL2. Yeah, I can get those. I mean, what I'm really excluding are so-called irregular elements. Irregular means that they don't have eigenvalues on the unit circle. So what's left in PGL2, if we exclude irregular elements, are elements which are torsion, which have all eigenvalues on the unit circle.
Yeah, that's. I mean, the conclusion is fine.
Yeah.
It's still not like evidence.
Okay, I should say elliptic. So, because in lattices they are torsion, but the limit can be elliptic. Elliptic and unipotent elements. Yeah, so, but on the other hand, Seven Samurai says that if nu is not trivial, then it gives positive mass. There is given subgroups. Yeah, and that means that if we combine those two, it means that nu has to be trivial.
What you explain here is the proof of theorem D.
Yes.
Manifold.
Yes, and here the proof of theorem D. So there is an analytic part.
So that's the orbifold case.
Yes, orbifold case and torsion.
Before we had torsion-free case.
Yeah, before I had torsion free, because I couldn't control the trace, the contribution to the trace that comes from torsion elements. So before this, I didn't know if the space, if these locally symmetric spaces can have like very large number of conical points. A priori, they could have number of conical points could be proportional to the volume, but it turns out that what you can always prove is that they have small number of short geodesics. And now this soft method used by Seven Samurai tells you that in the limit, the number of just conical points has to be small volume, just because conical points and cusps, just because of the elements of the group that correspond to those points form an element, they form a subset which is it's I won't say that it's not Zariski dense, but it's too small. It cannot support irises.
When does the convergence Benjamini-Schramm tell you about what happens at the boundary if the lattice is non-uniform? Do you get some sort of same equidistribution but with a larger constant as the volume grows?
About the boundary?
Yeah.
You mean if we look at boundary of the group of the lattice.
The boundary corresponding to the cusps.
The cusps. So Benjamini-Schramm convergence tells you that the number of cusps is small volume. Yes, that's
For instance, in the case of SL2Z, so the cusp is the quotient of the rational projective line by SL2Z.
okay.
And then you can get similar things in the other cases. I mean, the cusps are quotients of
Yes.
chorospheres, and you look at the boundaries of chorospheres. And then you have a certain family of points at infinity corresponding to the non-uniform lattice. And I was wondering if this Benjamini-Schramm convergence tells you something about how this some base points of chorospheres, say, equidistribute.
I didn't think about this. But if I understand correctly, those points on the horosphere, they are well defined up to.
Are quotients of horospheres by stabilizers in the lattice.
Yes.
And so you have a certain families of horospheres, finitely many, projecting on each of the cusps. So I was just, so for each non-uniform lattice, you'll have such a family. And my question was if this, knowing that you have this convergence, Benjamini-Schramm, tells you something about how those points behave in the boundary, say. I mean, they usually equidistribute, maybe they equidistribute to the same speed, but with a constant, multiplicative constant increasing with volume, something like that. Because it's the thin part, so.
Yeah, we can dive into detail. I'd like to see the picture to understand correctly.
So can you say a word about the theorem A? The proof you didn't say anything about
Yeah, but I'm over time.
Yeah. Are you for it?
Approve. If I'm allowed to.
People are allowed to leave, right?
So,
Right. About to say more about
of course,
proof.
I will be happy
should,
to allow people to say something about the proof.